Hey guys, and welcome to this video on the slope-intercept form of a linear equation. So let's do this. Alright, before we get started, a quick note on multiplication. In front of you, you see two multiplication problems, and I'd like you to take a moment to rewrite the following using addition. So recall, one way we can think about multiplication is when you multiply one number by a second number, the second number tells you how many times to add the first number to itself. So in 2 times 4, this means add 2 to itself 4 times. Or in -3 times 5, that means add -3 to itself 5 times. This is going to be really helpful during this section. Okay, also, recall a few of the examples where we took real-world situations before and made equations to describe them. So for example, the cooking club starts with 2 members in it in 2008. Every year that goes by, the number of members increases by 5. Or the PE department started the year, which is September, with 18 basketballs. But every month that goes by, they lose 4 of them. And I'd like you to take a moment to pause the video, and for each of these, identify the independent and dependent variables and create an equation to describe that situation. Now you may have chosen different variables from me, but that's totally fine. In our first equation, I had m equals 2 plus 5 times n. In our second equation, I had g equals 18 minus 4 times t. Now, the 2 and the 18 in the two equations represented the starting values for our dependent variable, when the independent variable was equal to 0. So the number of members in the cooking club in 2008, when it had been 0 years since 2008, or 18 basketballs in September when it had been 0 months since September. The 5 and the -4 represented the change in the dependent variable for a 1-unit increase in the independent variable. Of course, the number of members in the cooking club went up by 5 every 1 year, and the number of basketballs went down by 4 every 1 month. And we're going to be looking at similar types of equations now, but they're not going to be bounded by any restrictions that our modeling equations had, because our equations now aren't going to necessarily be describing any real-world situations. In this section, we're going to discuss equations that are all of a certain form, like the 4 you see below. Note, every single one of the equations we look at now is going to have a graph that looks like a line, as every single one will meet the criteria we talked about in the last section. And hence, these types of equations are called linear equations. Now note, in each of these equations, we have a variable by itself. And note, if we have an equation where one variable is by itself, most often that variable will be our dependent variable. Then we have an equal sign. We have some constant without a variable attached to it, either an addition or subtraction sign, and a variable being multiplied by a number. And when we multiply a variable by a number, we call that number a coefficient. That second variable will be our independent variable. Now, we are going to get some equations later on that don't necessarily look like this to begin with, but we're going to often change them to fit this form because this form makes it really easy for us to dissect these equations and later to draw their graphs. Alright, let's take a closer look at 2 of those 4 equations that we just looked at. W equals -6 plus 2k and y equals 7 plus 4x. And what we're going to do is fill out a table of values for each of these equations. First things first, for this w equals -6 plus 2k, since that w is by itself, that's most likely our dependent variable, and so k is going to be our independent variable. So let's quickly, explicitly write that down. And remember, once we know this, when we find ordered pairs for this equation, we usually cycle through values of our independent variable. Like you see on the right, we're cycling through values of x. So let's label this left table appropriately with the k going above these cycling values, because that's our independent variable, and w going above the blank column. Of course, all our ordered pairs for this equation are going to be k, w ordered pairs. So what I'd like you to do is to pause the video and fill out these tables of values for each of these equations. And as you go, see if you notice any patterns arising, because these patterns are going to be so integral to dissecting these equations now and graphing them later. Okay, Now that we have our table set up, the first thing I'd like to draw your attention to are the ordered pairs 0, -6 for our first equation and 0, 7 for our second equation. And if you look at the equations, that -6 by itself, that lets us know that when k is 0, of course w is going to be -6. And that's a really important ordered pair for this equation. And for y equals 7 plus 4x, of course when x is 0, y is going to be 7. And this tells us that when we graph these later, -6 is going to be the w-intercept for our first graph, and 7 is going to be the y-intercept of our second graph. So one more reason that this ordered pair is so important, but also really easy to find with this form of the equation. For our first equation, note that every time our input goes up by 1, our output goes up by 2. And that's because of this 2 in our original equation. That equation says w starts at -6 when k is equal to 0, and that k tells you exactly how many times to add 2 to -6. So if k is 1, add 2 1 time to -6, you get -4. If k is 2, you add 2 2 times to -6, you get -2. If k is 3, you add 2 3 times to -6, and you get 0, and on and on. In our second equation, every time our independent variable goes up by 1, our dependent variable goes up by 4. And that's because of the 4 in the equation right here. Note that this equation says y starts at 7 when x is 0, and whatever x is, that's how many times we're going to add 4 to 7. So if x is 1, we add 4 to 7 once. If x is 2, we add 4 to 7 twice. If x is 3, we add 4 to 7 thrice. If x is 4, we add 4 to 7 4 times, etc., etc. Of course, all this works in reverse too. Every time our input goes down 1 unit, in our first example, the output goes down 2 units. And in our second example, if the independent variable goes down by 1 unit, our dependent variable goes down by 4 units. Alright, let's look at 2 more equations. But before we find the ordered pairs for these two, it'll be a lot easier for us if we put these in the nice form of all the equations that we saw earlier. So in our first example, let's go ahead and put that into y equals form. In our second example, we don't know what our independent or dependent variables are yet. At first glance, it looks like it's going to be really easy to solve for q. All we have to do is divide both sides of the equation by 2. So let's call q our dependent variable and d our independent variable. So why don't you put these both into dependent variable equals form. Alright, and now we're ready to go ahead and find some ordered pairs. One quick note, for our first equation, y equals -2x plus 8 is exactly the same thing as y equals 8 minus 2x, but this latter equation, y equals 8 minus 2x, I think that's going to be a whole lot easier for us to understand later, so this is the one I prefer to use. Now I hope you feel pretty confident finding these ordered pairs for these equations pretty quickly, especially using the patterns we just discussed with our previous 2 examples. So I hope this is a breeze for you. Please find the ordered pairs for these 2 equations. Alright, now note that 8 in the first equation tells us what the y value is going to be when x is 0. Very important point, because especially if we were to graph y equals 8 minus 2x, 8 would be the y-intercept. So look how easy that is to find from our equation. In our second example, -4 is the value of q when d is equal to 0. If we were to graph this on a set of axes, -4 would be our q-intercept. Again, really important. In our first equation, every time our independent variable goes up by 1, our dependent variable goes down by 2. And that's all because of this -2 in our equation. This equation says y starts at 8 when x is 0, and x tells us how many times to subtract 2 from 8. So if x is 1, subtract 2 once from 8. If x is 2, subtract 2 from 8 twice. If x is 3, subtract 2 from 8 thrice. In our second example, every time our independent variable goes up by 1, our dependent variable goes down by 3. And that's due to this -3 in our equation right here. This equation says Q starts at -4 when D is 0, and D tells us how many times to subtract 3 from -4. So if D is 1, you subtract 3 from -4 once. If D is 2, you subtract 3 from -4 twice, and etc., etc. Of course, for both of these, that same process works in reverse. In our first example, every time our independent variable goes down by 1, our dependent variable goes up by 2. And in our second example, every time our independent variable goes down by 1, our dependent variable goes up by 3. Alright, so now we're ready to make some generalizations about the linear equations of the form we've been discussing. Here I have it in both the form that we saw earlier and the exact same thing, just with some variables, y equals b plus m times x. So for equations of this form, the first number, b, tells that the equation will have the ordered pair 0, b. Note that that's going to be an intercept when we graph this later. The second number, m, tells us that the dependent variable will change by m for every 1 unit increase in the independent variable. Now note that that change could mean increasing or decreasing. And this is a good time to define the slope of a linear equation. From the equation above, that second number m, the number that tells us how much the dependent variable changes for a 1 unit increase in the independent variable, is called the slope of the linear equation, or the slope of the line when we graph these. The slope basically says how quickly the dependent variable is increasing or decreasing. One more definition. The slope-intercept form of a linear equation. So whenever we see an equation of the form y equals b plus mx, which is my preferred form of it, or y equals mx plus b, we know that we're looking at an equation whose graph will be a line containing the point 0, b, the y-intercept in this case. Of course, if we were using variables other than x and y, it would be a different intercept for that variable, having slope m. Hence, this form of a linear equation is called the slope-intercept form. Alright guys, so at this point I hope you feel really confident putting these equations in a slope-intercept form and then using that to quickly find the ordered pairs for these equations. So 2 last examples to practice with. So why don't you pause the video, please put both of these into either y equals or b equals form and find the ordered pairs. Alright guys, that's it. Hope you enjoyed.